Today we're going to look more at exponential and logarithmic functions, and specifically we're going to talk about inverses. And before we get to inverses, we need to talk about the domain of a logarithmic function. Because unless you're coming from college algebra, you have not really explored the domain of a logarithmic functions, at least enough to master that concept from Algebra 2. We talked about it a day here and a day there. So we did a couple of examples here in one day in Algebra 2, and then we stopped. And then we did a couple more examples in another day, but it was nothing that I really think that we completely would have remembered. But if f of x equals a to the x, the exponential function, then the inverse. Remember, f to the negative 1 is represented by the inverse of that function is the log base a of x. It's the logarithmic function. And the thing that we need to remember about inverses, because we're going to talk about the actual inverse of an exponential and a logarithmic function today, is that when you find the domain of the original function, then the range of the inverse is the same as the domain, which is over here to the right. The domain of f equals the range of the inverse, f to the negative 1. Because in inverses, the domain and the range switch. The x and the y switch places. And that's the same thing here. The range of the original function became the domain of the inverse function. And we spent a fair amount of time in our last unit on that topic. So I think that that concept is going to come back to you pretty quickly. But what results from that then is that the domain of the parent logarithmic function is 0 to infinity. But what values do 0 to infinity represent? Well, what they represent is they represent positive numbers. Start at 0, but 0 is not included, but anything past 0 is. So for going to the right from 0 to infinity, all of those values to the right of 0 are positive. And so different teachers have different ways of presenting this. But when we look at a function where we want to find the domain of it, this value here, which is sometimes called the argument. Oftentimes, if you look up anything on the internet, it oftentimes is called the argument. And I sometimes use that word. But this part of the logarithm has to be positive if we're able to work with the problem at all. So to come up with the domain of it, we take x plus 3 is greater than 0. We solve that by subtracting 3 from both sides. We get x is greater than negative 3. And there, that's in set notation, but we could also write it in interval notation, which is mostly how I write it. But I'm okay with the other version. Just watch out on Math Excel, and we don't have one for you yet, probably next week. So, letter B, g of x is log base 5 of 2 minus x. To determine the domain, the only part of this equation that we need to look at is the part that I just circled. And that part has to be positive. So it's 2 minus x is greater than 0. And when we solve this, I'm going to leave my letter on the left. It's a personal preference. But it's just to remind you of something else as well. When we solve this, it's negative x is greater than negative 2. We're going to divide both sides by negative 1. And when we divide an inequality by a negative, what happens to our inequality symbol? It changes direction. And still, negative divided by negative is positive here, and negative divided by negative is positive there. And we get x is less than 2. If we write that in interval notation, it's negative infinity to 2. The 2 is not included. There's no equals in that symbolism there. One other thing to notice is it doesn't matter that it's log base 2, or it doesn't matter that it's log base 5, or it doesn't matter that it's log base 1/2. The part that we have to be concerned with is going to be this part right there. That part, again, sometimes called the argument. If you look up something on the internet that's going to talk about the argument, the 2x minus 5 has to be greater than 0. And we can solve this, and this time we're going to get a fraction or a decimal, but the process is still going to be the same. We're going to divide everything by 2. We get x is greater than 5/2, which if you prefer, you can write it as 2.5, you can write it as 2.5. It doesn't make any difference to me, but it's x is greater than 5/2, no equals, so everything's going to have parentheses. Infinity always has a parentheses, and the 5/2 doesn't have an equals, so it's going to be parentheses as well. And we're going to get still more practice with domain on these types of problems. It says, find the domain of f of x equals 3 log of x minus 1. Well, once again, when we start with this, looking at the domain, this part of the logarithm only is where we start. And that value, in order for me to fit it in, has to be positive. So we're going to solve it just like we did our previous 3. And it's x minus 1 has to be greater than 0. Because that part of the logarithm has to be positive. It determines the domain of the function. We can add 1 to both sides and we get x is greater than 1. And if you prefer, it's 1 to infinity then in integral notation. So we found the domain of this function. Now let's see what we remember from our previous units here. It says what transformations occur to the parent function of y equals log of x to create that function. So in other words, what does 3 in front of the function do to the function? How does it transform it? And it is. It's a vertical stretch. And then what does the minus 1 inside the function, how does it change that function? And hopefully you're thinking, right, 1. And part C here says to graph it in the calculator. Now, it doesn't matter what calculator you have. The log button on your calculator is the basic log button on your calculator. Let's get out of there for a second here. Whoops. Is over here to the left. That's the log button that we're going to use. To the left, beside the button number 7, for those people watching on the video. But if we want to type this in, we're going to go to y equals, we're going to type in 3 log of x minus 1. And we can look at the picture, but really more specifically what we want is the table to give us a couple values to graph. So we can go to second and graph. That gets us to the table here. And you can see that we've got errors before 2, because we're not going to have any values in the graph at that part. So I'm going to scroll down here the best I can for a couple of seconds. See if we can find a better second point to graph besides the decimal there. And it's nice that this screen shows up, shows a few more values than some of the other screens. So in particular here, as we're graphing, let's graph the point 2, 0, and the point 11, 3, which I know goes off our graph a little bit. We saw the picture just a minute ago, but the bottom line is that that graph doesn't stop like it stopped on our calculator. It's just that because of pixels on the calculator screen, it looks like it stops. Again, the points I graphed were 2, 0, and 11, 3, which is off our graph. You can graph some other points in between because you've got your calculator to look at that. And what we want to come up with now is, what is the range of this function? Well, when we look at these values, we see that we've got part of the graph that's below the x-axis graphed, and we've got part of the graph that's graphed above the x-axis. So the fact that we've got points that are below the x-axis and above the x-axis means that the range of our function is going to be all real numbers. Negative infinity to infinity. We have an asymptote in this graph, and the asymptote is actually, and I have to scoot it over a little bit, roughly there. Let's see what I can do to move it over. Remember how the domain and the asymptotes go together. So we have x is greater than 1. Well, let's then say that we got x equals 1 for our asymptote. We're never going to be to the left of that line, and that's why we saw when we pulled it up on our screen a bunch of errors, because we're not going to have any values there. On this particular graph, I see an x-intercept, but I don't see a y-intercept, because we're not going to be graphing part of that. So our x-intercept is 2, 0. So now, algebraically find the inverse. And I know it says algebraically find the inverse, and I want to algebraically find the inverse. But just like our unit that we talked about for inverses, there's a few of you out there that said, well, can't I just graph this first and then come up with the inverse? For instance, 2, 0 is the same thing as 0, 2. We flip the x and the y. Or this other point over here, 11, 3, is going to be the same thing as 3, 11. And we're going to draw our picture there. And I missed it a little bit. But don't leave the problem blank just because you can't find it algebraically, and I hope that we can find it algebraically. But once again, inverse. Switch the x and the y. This point is 2, 0, so then I graphed 0, 2. The other point that we graphed in our blue graph was 11, 3, so then I graphed 3, 11. Switching the place values of x and y. But we really do want to figure out, how do we find the inverse algebraically? So the first thing that we do with our function here that I can't see yet, but instead of writing f of x, write y. So this is y equals 3 log of x minus 1. And then we're going to switch the x and the y. Well, when we do, x goes here, and y goes there. Nothing else changes places. X equals 3 log y minus 1. But in order to solve this, we're going to have to convert this logarithmic back into an exponential. And what's implied in that is we need to know what's the base of a logarithm when there's nothing written. And you should be going 10. You should be saying 10. So this is 3 log base 10. Now, if you're taking notes, make a note to yourself. I'll even write, if there is no base written with log, then the base is 10. I tend to get too wordy when I write that. But if there's no base written, when it's log, I should even be more specific, but I've got log there in the words, then our base is 10. But what we're trying to do is we're trying to algebraically find this inverse, and in order to algebraically find this inverse, we've started off good, we've switched the x and the y. We need to convert this to an exponential, but before we can convert it to an exponential, we have to isolate the logarithm. So what that means for us is we need to divide this side by 3 and this side by 3. So now it's x over 3 equals log base 10 of y minus 1. And remember what a logarithm is. It's another way of writing an exponent. So we're going to convert, but whatever the logarithm equals, that's going to be the exponent. So this problem is going to be 10 to the x over 3 equals y minus 1. And now we're almost finished with finding the inverse. So to complete our inverse, we're going to add 1 to both sides. And now we're going to have our inverse, which is 10 x over 3 plus 1 equals y. By the way, remember our inverse notation, that's f to the negative 1 of x. And the nice thing is we've got a good calculator that's going to graph this for us. Because that's what our next part says. And we already have it here. We know what it's going to look like, but let's look at a more precise graph. So it's 10 to the x divided by 3 plus 1. Notice you don't have to use the fraction button for your exponent, but you can. And there we get that. Which again, if you compare back to what we had originally, it looks like that. There's that. Here's the picture on our paper already. Does this graph reflect over the line y equals x? Remember y equals x? Goes from the bottom left-hand corner to the upper right-hand corner through 0, 0. In other words, if we fold this graph over that green dotted line, will the blue graph land on the red graph? Yes, exactly. So yes, it reflects over the line y equals x. And then lastly, what we want to come up with is we want to come up with the asymptote. We want to come up with the domain and the range, all of the inverse. Well, once again, it goes back to the inverse. The whole underlying concept of inverse is that you switch the x and the y. In our original function, our asymptote was that purplish color line, which is x equals 1. Well, in our inverse, then we're going to switch the x with the y. So we get y equals 1 for our asymptote. The domain of the inverse is coming from the range of the original function. The range of the original function is negative infinity to infinity. So our domain is going to be negative infinity to infinity. The range of our inverse is coming from the domain of our original function. It's the very first piece of information we came up with, which is 1 to infinity. Remember, the x's and the y's switch. So our range here is going to be 1 to infinity. So as we turn our papers over and we look at the back, what we've got is we've got a natural log, ln. And the thing about the domain is whether it's spelled log or whether it's abbreviated ln, the domain is calculated the same way. This part of our logarithm has to be positive. So when we go to find the domain, we're going to take x minus 2 and set it greater than 0, add 2 to both sides, and we get x is greater than 2. If you want to leave it in that format, leave it in that format. But here's the interval notation. When we go back and we look at the transformations here, what does a negative in front of the function do to the function? Well, it reflects. Think to yourself at least, does it reflect over the x or does it reflect over the y? And hopefully you're thinking x. One other transformation here, we have x minus 2. Well, what direction do we move when we see minus? Well, we're going to go right, 2. But once again, the nice part is that we've got our calculators that we can use to help us type in. And unfortunately, on this particular problem, the numbers aren't going to be as nice for us, but it'll still be okay. So we type it in. And off to the left of your screen, kind of beside the number 4, the 4 button is where you see the ln button. So it's going to be negative ln, and then it's going to be parentheses, darn it, x minus 2. And we can look at our picture. So there's our picture. But really, more importantly for us, let's look at the table. And I'm going to start back here at 0. We don't necessarily have as nice numbers. We're going to have to graph a decimal number, but let's do the easy one here, 3, 0. I'm going to put the table here so we can see it. 3, 0. And then the other one that I graphed, and it's up to you, but negative 2.079 at 10, 10, and then a little bit more than that. And our function, it still goes down like this, even though our screen doesn't show it as well. But there's a rough picture there, and I think that I just drew it wrong because I didn't graph negative 2. Let me try that again. 3, 0, that was right. But it's 10, negative 2 point. So this way. So we're going to go here now. My curve is even better than the last one, so that worked out for the best. So there's our picture. Again, you could have picked some other point to pick. You could have picked 5, negative 1.099. Just get a couple points on there so that you can have a rough picture. You've got a calculator that's going to show you a good value. We calculated our domain of this function. Well, what do you think the range is going to be? And we've got values above the x-axis, and we've got values below the x-axis. We've got a value on the x-axis, which means that our range is going to be all reals. Let's do the intercept here real quick. And the intercept, well, we only have an x-intercept that we can see, 1, 2, 3, 0. But we do have an asymptote, and it actually is here. And the reason that I know that it's there is I went back and I looked at the domain. And the domain says 2 to infinity. And that's why I put our vertical asymptote on the 2. So this one is x equals 2. Now once again, I am going to find this algebraically. But for some people who struggle with the algebra, I want you to at least be able to draw the graph. And what has to happen here is you get 3, 0. So, 0, 3. The other point that I graphed on here was 10, negative 2.1, roughly. So then I'm going to have to go negative 2.1, 10. And when we draw this picture here, it looks roughly like that. The question is, does that make sense here if we put in the line y equals x, even before we find that algebraically? And I'm a little bit off on there, but does it seem logical? I know I'm a little bit off on my graph, but maybe your picture is better than mine. And we'll look at this in a minute on our graphing calculators too. But it seems reasonable. But what we need to do to find our inverse here, algebraically, is instead of writing k to the x, write y. This is going to be y equals negative the natural log of x minus 2. And we switch the x and the y. X goes here, y goes there. And this time what we need to know is what's the base of a natural logarithm? Somebody said it. It's e. And we, like the last problem, need to isolate the logarithm in order to convert it to an exponential. And it's kind of a little tricky here, but it's this negative. We need to deal with that negative. And what's going to happen is we're going to divide this side by negative 1. And we're going to divide this side by negative 1. And we end up with negative x equals natural log of e, and then y minus 2. If we can get the base written in there, we can get the logarithm isolated, then we can come up with the rest of what we need to come up with our inverse. Remember, a logarithm is another way of writing an inverse. So this is going to be e, whatever the logarithm equals, and I said it wrong. A logarithm is another way of writing an exponent, so whatever the logarithm equals is the exponent. It's going to be e to the negative x equals y minus 2. And now we can finish here by moving the 2 over to the other side. And we have e to the negative x plus 2, and that's our inverse. And part F, then, says, let's look at a more precise picture. So we have the first one in there already, but now let's type in e to the negative x. So I'm going to go second ln, that'll give us e to a power. You also have the e button on your division bar. You can go second and the division button, but e to the negative x, either way you get there, and then arrow plus 2, and we can look at our picture. So a little bit better there for me. And in fact, if we put in for our third equation y equals x, that picture, like I said, is better. The one flaw here is that we need to keep that going there. But now it's a really good picture. And then we can answer some questions about this. So it says state the intercepts of our inverse, which is our red graph here. Well, we only have one, and it looks like it's 0, 3. And let me stress again, inverses. We switch the x and the y. So when we switch the x and the y, here originally our asymptote was x equals 2. So now it's going to be y equals 2. The domain of the inverse is coming from the range of the original function, which is above here. The range of our original function is negative infinity to infinity. And finally, the range of our function, of our inverse, is coming from the domain of our original function, the very first part that we found on this function, which is 2 to infinity.